We will make a start on today's session then. So, what we're going to have a look at is AC analysis, so analysis of an AC circuit with capacitor and inductor in using Thevenin's theorem. So drawing the circuit on the board, we got a 100 volt AC supply, 6 ohm resistor and an 8 ohm reactance inductor. So I've given you the reactances. I haven't given you the inductance in Henrys and I haven't given you the capacitance in farads. Therefore, you don't need to know the frequency of this voltage. Okay, and then we got a parallel capacitive reactance of 3 ohms, and across that we've connected our load resistor, which is the resistor of interest. Yeah. So remember, Thevenin's is useful where we want to be able to analyse how that circuit to the left of my piece of paper there reacts to different load resistors. We're not going to do that today, but once we've done the Thevenin's equivalent circuit, we can plug in any load resistor we want and analyse how that circuit delivers power to it. Okay, so all we're going to do here is use Thevenin's theorem to find IL. The actual process of going through Thevenin's is no different. You do the same stages, just that you're dealing with complex values as opposed to just normal DC values. So, has everybody got the circuit down? Right, so what is the first step then in the process of going through the Thevenin's theorem? Remove the load resistor. Yep. So first step is we take away the load resistor, leaving 2 open terminals. Hang on. So we're on step 1, which is essentially finding V little t, the Thevenin voltage. So having taken out the load resistor, leaving 2 open terminals A and B, what do we then do? So you remove load, what's the next stage in step 1 of the process? I'm looking for the overall thing that you want to do. It's related to these 2 open terminals A and B. Remember, what is the Thevenin's voltage? Just let me add a page in here. Ultimately, the Thevenin's equivalent circuit that we're aiming for looks like this, remember. It'll be an AC voltage of voltage V little t, a single series resistance of R little t, and our 2 terminals A and B. So that part will replace the circuit we got on the other page with the load resistor. So the Thevenin's process is going through calculations to determine this voltage VT and that resistance RT. We can then connect our load resistor back in there. What was RL? 50 ohm, 25. We can connect that in, and then that simplifies the calculation with the current because we've got lower. Yeah. So if you want to analyse for a range of different load resistors, you can do it much quicker by doing the tricky calculations once than using the equivalent circuit. Alright, so that's eventually, when we've done our calculations, we'll come and add these two component values to this, and then we can use it to calculate the current. So, next step in the process then, yeah, you're right, we take away the load resistor, but then what do, having done that? What overall are we going to do? VT equals what? It is about a volt drop. What you should be remembering, and you do need to know this process, because in an exam question about Thevenins, I'm going to be expecting you to properly explain the process and not just do it. Okay? But the Thevenin voltage is this voltage here when the load resistor is removed, the open circuit voltage. So that's V little t across there. The open circuit voltage when the load resistor has been removed. Yeah? So let's make a note of that there. Little Vt is equal to open circuit voltage at AB. Yeah. So now we've got to go through the maths to find that open circuit voltage. What voltage would that be equivalent to? Where's current flowing? In that circuit as it stands, where have we got current flowing? Yeah. What about here? No current, exactly. Yeah. So, because there's no current flowing, if you look here, would you not say that you've got VC dropped across there? Yeah. And in that section there, you've got an infinite resistance here, but you've got a Kirchhoff's voltage law loop that will say that there's a clockwise arrow, one anti-clockwise arrow, those two voltages must be equal to each other. Yeah? So if we can find VC, we've got VC, because they're equal. All understand that? Yeah? So how are we going to calculate VC? Where can we start to find that voltage VC? What formulas do you know that will allow you to calculate from the VC with what we currently know? You can use it. Yeah, you're on the right track now. First, you need to find the current around this loop. Once you know the current, you can use that reactance to find VC. What else do we need to know to find the current? Total impedance. Yep. So here we go. First find total impedance ZT is equal to. So what kind of circuit we got there? How can we calculate its total impedance? They're all in series. So the impedance of the resistor is R. The impedance of the inductor is impedance of the capacitor is. What do we need to be careful about there though? Yes. XL is a positive value. XC is a negative value. And what else have we got to include? Yeah. Those two times J. So it's a full formula for RLC total impedance. Yep. So now we can put our numbers in. Resistance is 6 plus XL is 8, isn't it? Minus 3 J ohms. 6 plus 5 J ohms. Alright. At some point we may need to convert that to polar form. So it's probably a good idea to do it now. Convert that to polar. .81 ohms angle 9.8 degrees. Yeah. So that's the total impedance. Now we can calculate the current from, therefore, I is equal to E over Z T. That's the 100 volts. Angle 0 is assumed if you're not given one. Over 7.81 angle 39.8. The result of that is 12.8 amps, remember, angle minus 39.8 degrees. A point to make here is that XC here, 8, is greater than XL is greater than XC, so overall this circuit is inductive. Yeah, it's got capacitance in it as well, but overall that's inductive. So using that word civil, we've got an inductive circuit, we've got the current's got a negative angle, that's lagging the voltage. Yep. So that's a useful little check that you've done that complex division properly. Yep. Okay. So now that we know the current, we can say that VC, which is also equal to our little Thevenin's V little t that we want to find, is equal to I times XC. I is 12.8 angle minus 39.8 degrees. I usually put these in brackets. We're going to multiply that by the XC, which is 3 ohms. What's the angle associated with a capacitor? Minus 90 degrees, yeah? So we do that multiplication and we get a V little t equal to, so we got 38.4 volts angle minus 129.8 degrees. So that is our Thevenin's voltage. So on our equivalent circuit I drew, we can now write that in. V little t is equal to 38.4 volts angle minus 129.8 degrees. Yeah. So we got that on. We got one part of our equivalent circuit. So from that diagram, what's the next step in the Thevenin's process? From that diagram, what do we do next? Step 2. Overall, we need to find R little t. But what do we have to do that? Some revision is required, I believe. Yeah. So what do we do now? How do we find R little t? No, that was that's the typical impedance. Actually, you've got a point that really ought to be Z little t. Yeah. That should be on here as well, yeah, on this one. Oh, no, you didn't, because Z total of that circuit. Don't get them. That's why I used the little t for the Thevenin's equivalent values. Yeah. Alright? All you're doing there is finding the total resistance of this loop with respect to that voltage. Thevenin's is different to that. Alright? ZT, Z little t, is the resistance looking in there, yeah, when you replace all sources with their ideal internal impedances. Yeah. So you take out any voltage sources and any current sources you've got in the circuit, and you replace them with their ideal, the resistance of an ideal voltage or current source. So what we do is, in this case, remove source and replace with short circuit. That's the impedance of my ideal voltage source. That's what it is. So we do this, we go bugger off voltage source, replace him with the short circuit. And now ZT is the impedance looking back in from the terminals A and B. A completely different impedance to the total impedance we calculated earlier to calculate that current. Can you see that now? Before we were looking from here, now we're looking in from completely the opposite end. So how are them components arranged in terms of this looking back in this way? What type of circuit we got? In terms of parallel series. Yeah, what we've got we've got Z little t is equal to XC in parallel with XL and R in series. Yeah? We've got a parallel circuit with XC being one run. What you're doing is thinking, if I connect an ohm meter to here, which has got a battery in it that's trying to pass current, that current is going down here, some of it's going down the capacitor, and some of it's going through the inductor and the resistor. So you've got those two components in series, so we add them together, and that's in parallel with that one component there. Yeah. So we've got to do a parallel calculation, a series calculation. So let's have a look at doing that. What we'll do is we'll use product over sum. Yeah. So we've got RL plus XLJ. That's the two components in series. I'm going to multiply them by 0 minus 3J. That's the capacitor. That's the resistor and XL in series. Yeah, added together. Right. That's the capacitive reactance on its own. Right. And then the bottom will be all three added together. So it'll be R plus XL minus XC J. Yeah. Now we want to multiply. Let's just like that. Like that. We want to multiply two complex numbers together for the numerator on the top. So we really want them in polar form. So we want this is a resistance is 6 plus 8J is that bit, multiplied by 0 minus 3J capacitance underneath 6 plus 8 minus 3J. We want to convert these into polar values now. So convert each of those individually into polar values. We've already got the bottom in polar value from earlier. That was the total impedance series wise was 7.81 angle 39.83. So we already calculated that. But on the top we need these two numbers converted separately to rectangular polar form. And that is times, we don't need to calculate for that one. The capacitor is 3 angle minus 90 degrees. Yeah. And then if we multiply out the top line, the numerator, what do we get? I agree with 30. Careful. Minus 36. Yep. And now we do the division. Now we do the polar division. So the final answer for Z little t is equal to I've got 3.84 angle minus 76.7 degrees. Yep. Okay. So we can now put that value on our equivalent circuit. So that's 3.84 angle minus 76.7 degrees. Okay. So now we've got a relatively simple single voltage, two components in series calculation to be able to find the current. Yeah. So we can say the current I is equal to V little t over Z little t plus RL. If we want to add Z little t to RL, what form would we like Z little t in? If you're going to add them, rectangular, yeah. So we'll leave V little t at 38.4 volts angle minus 129.8. Yeah. But convert ZT into rectangular form. We'll go back again in a minute as well, but 0.883 I got on my version pan, yeah. 0.74 J. Yeah. And we're going to add to that 25 plus 0J for the resistor. Yeah. Complex number addition. What do we do? So we'll keep that at 38.4 angle minus 129.8 degrees. Add them two complex numbers together. What do we do? Nope. We add the real parts and add the imaginary parts separately. Yeah, so we go 3.74 plus 0.883. Yeah. Minus 0.74. Yeah. Now we want to put that denominator back to polar form. take 26.2 then, angle nearly done it again. Yep. And then the result of that division is I've got 1.47 amps angle minus 121.6. Might be slightly different, but somewhere around that. Yeah. Right. Now, our voltage is at angle 129.8 minus, and our current is at minus 121.6. Not so easy to see the check here, yeah? But if we consider our angles on a axis, yeah, and our voltage I'll put in red is minus 129, so that's 90, minus 129, somewhere there. The current in blue is negative as well, but less than that, so that's here somewhere. I. And we go round that way, so current is leading voltage. Has to. Yep. All right. Yeah. So you're all happy with that and that process? And that's the same process as we use for DC circuits using Thevenins. It's just that the numbers are a bit more tricky, and there's this converting between polar and rectangular form to be able to do the maths. But other than that, the process is the same. We take the load resistor out, find the open circuit voltage, that's the Thevenin's equivalent voltage, and then we take out any sources. So if there's multiple sources, you have to take them all out. You replace a voltage source with a short circuit, you replace a current source with an open circuit, and then you look for this impedance or resistance in the case of a DC circuit, looking back in at the terminals AB. So get that process in your mind so that you can explain it as you go along and you answer the question. Yep, in the exam.